right? If we are going to develop our method for dissolution, right? So these are the goals for which purpose we are going to develop our methods, right? If you are seeing any monograph, particularly with respect to the IP and USP, so if you are seeing any monograph on any API, they are generally written a procedure with respect to the assay, related substance and dissolutions. And there are many tests with respect to identification as well, right? So before going to start a method development, we are generally focusing on goals, right? In your M.Pharm dissertations, generally students are focusing to develop a method for the estimation of these compounds. Like they are focusing to estimate a assay. Okay. So after that, we should focus on the nature of our sample, right? Uh, for we can say that if I wanted to develop a method, right, for a particular compound, right? So there are list of information I have before going to start with the method development, like nature of compound, whether it is in acidic in nature or basic in nature. Okay. Then after uh, we can say uh, what is the pK of that particular compound, right? What is the solubility of that compound? Okay. What is the UV lambda max of that particular compound, right? Stability. So this type of information that we have to gather before going to start method development. Done. The next thing is selection of detector. It is generally depend upon the nature of your sample. If your sample doesn't have a chromophoric group and you are selecting a UV detector, then you are not getting any peak in your UV detector. Okay. So for that purpose, you have to select the refractive index detector if possible. So according to the nature of your compound, you have to select a detector, right? The next thing is selection of mode of separations. As we all know that there are two mode of separations. The one is normal phase HPLC. The second is reverse phase HPLC. According to the nature of our sample, we are selecting a one of, right? So if my compound is having organic acids, right? So generally we are preferring a normal phase HPLC. Okay. So according to our nature, we are selecting a mode of separations. In that we are selecting a column and mobile phase, right? Because if we are using a non-polar column, then it is known as the reverse phase HPLC. If we are using a polar column, then it is known as the normal phase HPLC. Okay. The next thing is perform preliminary separations along with degradation study, right? Degradation study is nothing but we can say it as a forced degradation study, right? Forcefully we are degrading our samples and we are generating the impurity and we are injecting this sample to our chromatography to see that my method is capable of separating all these generated impurity or not, right? Or else my interested analytes, it is separated from this all impurity and we are getting the peak purity or not, right? So this type of parameters that we have to check during the method development while injecting or while degrading our samples and injecting to the HPLC, right? It is nothing but we are confirming a selectivity and specificity of the method. Of course, we are generally doing this parameter at a validation stage, right? But before going to start a validation, we have to confirm that test during our method development as well, right? Some of the students are correlate this degradation study with respect to the stability studies and all, right? But the stability studies, if we are putting our samples in accelerated stability stations like 40 degrees 75% long-term stability stations, and during the different time interval like 1 month, 2 month, 3 month, 4 month, we are just taking out that sample and analyze this sample as per our method, and we just see a degradations of assay, or we can see the generation of any impurity. These are known as the stability studies, right? But here we are performing the forced degradation study. Forcefully we are degrading the samples. Okay, so these both things are different. In our title we are generally written over here like stability indicating RPHPLC method. So in that case we have to perform the forced degradation study and prove that my peak is separated from all these degradations peak, right? And there is my peak is pure. Okay, then and then we are able to write this stability indicating nature of our method. Once we are deciding all these things, we are started a optimization of conditions. Okay, after optimizations we are done a validations according to the ICH Q2R1, right? So these are the general strategy we can use for any method development, right? The next thing is what is known about the sample. If I am giving you any compound and tell you that you have to develop a method, right, for the assay determination of this compound. So if you have a sample, if you have a name of that particular API, then what are the information that you will get? The first is chemical structure of that compound. Okay, you can uh, search on various search engines and getting this chemical structure, right? Molecular weight as well, pK of that compound, right? UV spectra of that compound. If you are not getting a UV spectra, right? So you may dissolve that sample in different solvent like methanol, ACN, water, and take a UV spectra, right? And getting some lambda max value. Then after solubility of that particular sample, in which solvent my compound is going to be solubilized. Then stability, whether my drug is stable uh, in a light or not. We can say that light sensitive drug or not, right? Whether my drug is stable in a presence of moisture or not, in a presence of various solvent or not. Okay, so these all information we are getting while referring a MSDS, material safety data sheet of that particular compound, right? The next thing is concentration range of compounds in a sample of interest. Okay, what it indicate? Suppose I am going to develop a method of any tablet having a label claim 5 mg, right? So it is known for me how much amount of this API is going to be present in that particular tablet, right? So according to that, I have done various dilution and all, right? So the concentration range of compound, it is also a known parameter to start the development, right? If we are going to develop a method for the related substance, right? As we all know that impurities are generally present in a very minute amount. We can say it is in ppb level, nanogram level, or ppt level as well, right? So according to that, we are generally changing the instrument. Uh, if I wanted to uh, identify a impurity having a nanogram level, then generally I am preferring a LCMS-MS, right? If I am going to estimate the assay of PCM tablet, then I am preferring the HPLC. According to that, we have to change. Okay. The next thing is why use a buffer mobile phase? Why use buffer in our mobile phase? Generally, in uh, academic, students are not to prefer a use of buffer in their mobile phase. They are generally starting uh, uh, selection of mobile phase like water, ACN, water, methanol, right? If they are not getting a proper region, after that they are focusing to introduce buffer in their mobile phase. Okay, but in industry they are generally focusing on reproducibility of results, right? So for that purpose, they are introducing a buffer in the mobile phase. Okay, as we all know that when we are using a water and only methanol, right, there may be the chances of fluctuating the pH of mobile phase, because from where you are done these analysis. Suppose we can say that if I am using a water of my lab, right, it having some pH. If I am using a water of another lab, it having some another pH. So fluctuation of these pH, uh, that fluctuate RT of our analytes. So we are not getting a reproducible chromatogram. And in industry, it is crucial to have a reproducibility in the terms of RT as well. Okay, so they are introduce a buffer, and they are by using the buffers, uh, as we all know that buffer resists the pH change, right? So by introducing buffer, we are fixing out a pH, right? And by fixing this pH, we are generally obtaining a reproducible chromatogram, right? That's why a buffer incorporated in industries. So as I have written over here, when separating the acid and base, it helps to maintain consistent retentions and selectivity, right? Resistance change in pH so that analytes and silica can be continuously ionized, resulting in reproducible chromatogram. Generally, we are using a buffer range having 10 to 50 millimolars, not more than it, right? Because if we are increasing a buffer concentration in our mobile phase, that there may be the chances of reprecipitations, right? If we see the mobile phase, it's going to be hazy, right? And these precipitates are going to be deposited in our columns, and our column is going to be dead. It is no longer used. So that generally we are using a buffer in a concentration of these 10 to 50 millimolar. Understand? In this slide, I have uh, uh, written over here a list of buffers generally used for the HPLC, right? Certain phosphate buffers are used, like potassium dihydrogen orthophosphate, dipotassium hydrogen orthophosphate is there. Then after citrate buffer is there, acetate buffer is there, borate buffer is there, right? According to the pH range, we have to select a buffer. If I wanted to select a pH of my mobile phase at a range of 2 to 3, then it is more suitable to use phosphate buffer, right? Because at that pH, a phosphate buffer having a buffer capacity to resist the pH. Okay. So according to the pH range, we have to select a buffer. Not only it will depend upon the pH range, but also the UV cutoff range, right? Each and every buffer having a different UV cutoff range. Okay, phosphate buffer having a 210 nanometer, citrate buffer having a 250 nanometer. Suppose I have a compound that have a lambda max at 250, and the separation of that particular compound, I am using a mobile phase having a citrate buffer, then there may be the chances of interference with respect to the mobile phase. Okay, so we are not getting a proper results during the analysis, right? So UV cutoff is one of the important. Done. The next thing is understanding of pKa. What is the importance of pKa during the method development, or we can say the selection of pH or mobile phase? First of all, what is pKa? Right? The question is arised. The pKa is nothing but if we are selecting a pH of mobile phase that is equal to the pKa, at that pH, we are getting 50% of our drug is in ionized state and 50% of our drug is in non-ionized state, right? So if we are selecting a pH that similar to the pKa of that particular compound, right, then we are not getting a proper shape of our peak in a HPLC chromatogram. We are getting a tailing of peak, we are getting a broadening of peak, like issue we have observed, right? So it is ideal that you should select at least 2 pH unit different from the analyte pKa, right? suppose I have taken example like if I have a drug and that having a pKa at around 5, right, then it is more suitable that I have selecting a pH at a 3, means 2 pH unit different from the pKa, right? So what happening if I am using a 2 pH different from the pKa, right? The first thing happen is whether my 99% of drug is in ionized state or whether my 99% of drug is in unionized state. So whatever the tailing issue is that with respect to the that compound or peak broadening issue is there, we just overcome while selecting this pH, right? So based on pKa value, we are generally selecting a pH of our mobile phase, right? That's why pKa value of any compound is important. So the impact of pH on method development. As I told you that pH is one of the play a crucial role in the method development, right? Generally, we are using a reverse phase HPLC, right? And as you all know that in a reverse phase HPLC, our mobile phase is polar in nature. So generally, we are using water, methanol, ACN as a solvent of our mobile phase. And our column is in non-polar in nature, means it is C18, C8 in nature, right? So if we want to separate our acid base, means mixture of compound having acid and base, so pH play a crucial role in determining the retention and selectivity and in controlling the reproducibility and ruggedness of our method, right? In reverse phase HPLC, we are generally preferring a pH that having a lower inside, means in acidic side, right? 1 to 4 or below the 4, we can say, right? So while doing a lower pH, we are generally getting a reproducible results and we are eliminating this issue like tailing and broadening and all. Okay. As we all know this tagline, like dissolve like, right? Non-polar interact with the non-polar compound and polar compounds are interact with the polar compounds, right? And we all know that in our RPHPLC, mobile phase is polar in nature and our column is in non-polar in nature, right? And if we are selecting a pH, right, that ionize our 99% of our drug, right? So these drug that having ionized in nature, right, that interact with mobile phase and eluting first, right? And the drug, those are in non-ionized state, means non-polar in nature. They are interacting more with column and retain, right? And we are getting a longer retention of that particular compound. Okay. So based on that ionizations, based on the selection of pH, we are getting a proper RT of each and every compound. Okay. So increase and improve the interaction with the stationary phase lead to the higher distribution constant value and generally improve the separations. Natural analytes are more non-polar than ionized analytes. So it will improve the retention on the non-polar type stationary phase. Okay. So keep in mind this tagline, like dissolve like, polar likes polar, non-polar likes non-polar. Okay. Just take some examples that clarify you, right, in a simple manner. Suppose my compound are in acidic in nature, right? So I have a acidic analyte, and if I am using a acidic pH of my mobile phase, that is 2 unit below the pK of my drug. So what happened with respect to my compound in that mobile phase? My whole drug, right, it is in unionized form because acidic compounds are generally unionized in acidic atmosphere, right? Acidic compounds are ionized in basic atmosphere and basic compounds are ionized in acidic atmosphere, right? So my drug is unionized in nature, so it will interact more with stationary phase, means column, right? And by this way I am improving the retention of RPH on RPHPLC, right? So we are getting a longer retention time, means RT of that particular compound, right? And what happen if acidic analytes remain present in more basic environment? Means if I am selecting a basic pH of a mobile phase, then what happen with respect to the acidic analyte? Then my compound is in ionizing nature, right? So 99% of my compound is in ionized form. So ionized form are generally considered as a polar in nature. So it will interact with the mobile phase rather than interact with the stationary phase, and it is eluting faster. And by this way, we are reducing the retention time on RPHPLC. Understand? It is vice versa with respect to the basic analyst as well, right? Basic analytes, and if we are selecting a acidic atmosphere, means acidic mobile phase, then it is ionized in nature, right? And we are, by this way, we are reducing the retention time of basic analytes on HPLC. The similar, like if basic analytes is there and we are selecting a basic atmosphere, right, means basic mobile phase pH, then that will the drug will remain in non-ionized state, and it is more non-polar in nature, interact with the stationary phase and improving the retention, right? So what we should remember, we should remember that do not use pH equal to its pKa. Okay, this is the standard tagline that you have to remember during your method development, right? And what happened with respect to the non-polar compound, what happened with respect to the polar compound, right? These are these two general tagline. If non-polar compound are in non-polar in nature, it will retain on RPHPLC and eluting later. If compound having a polar in nature, it will not retain in RPHPLC and eluting speedily, right? First. The next thing is selection of detector, right? As we all know that there are so many detectors generally used or aligned with the HPLC modules, right? The first and well known is UV detector is there, right? The another is refractive index detector is there, ELSD detector is there, evaporative light scattering detector, fluorescence detector is there, electrochemical detector is there, and mass detector is there. If we are incorporating mass, it is known as the LCMS, we can say, right? So according to the nature of our compound, we are generally selecting a detector, right? If our compound having a UV absorbance, means having a exochrome group is there, chromophoric group is there, then generally we are preferring a UV detector during our method development on HPLC. If our compound doesn't have any exochrome group, or we can say uh, not conjugated double bond, right? So at that time we are generally preferring refractive index detector, right? Those compounds which are not giving absorbance at UV radiation. So according to the nature of compound, we are selecting a detector in method development. So what are the criteria that we should keep in mind for the selection of detector? The first is chemical nature of analytes, right? And its potential interference. The second thing is limit of detection is required, right? If I wanted my method that having the lowest LOD, limit of detections, right? So it would be not happen when we are using the RI detector, when we are using the ELSD detector, right? When we are using the PDA detector. So what level of limit we can use for the detections, right? According to that, we should select our detector as well. So it is one of the important parameter, right? The next is availability and cost of detector. The first is UV visible detector. As I told you that the analyte must absorb UV radiations, right? Then and then we are going to use this detector with HPLC, right? And as we all know that it is most widely used detector, right? Most of the compound absorbed at low UV as well, right? And if we have a PDA detector, right? Then we can monitor multiple wavelength, not a single wavelength, right? When we are dealing with these force degradation studies and all, right? Generally, we are preferring the PDA detector because we don't know whatever the impurity is going to be generated during the force degradations, at which lambda max they are going to be giving us the response, maximum response. So at that time, if we have a PDA detector, then we have to monitor a multiple wavelength with respect to the impurities as well, right? So with respect to this particular force degradation study, it is necessary to have a PDA detector with your HPLC module, right? The similar is choose the detection wavelength that maximize the sensitivity and specificity. Select the mobile phase solvent that have a UV cutoff, as I told in my previous slide, right? Some of the solvent, like we can use the methanol that having a 210 cutoff, ACN that having a 190 UV cutoff, right? So these all solvents are suitable when we are dealing with the UV visible detector. Okay, reduce the sensitivity, add to the baseline noise. If we are using a solvent or a buffer that have a higher UV cutoff, then what happen? You are generally observing that a noisy baseline, right? It is nothing but if you are using a buffer that having a higher UV cutoff, then you are getting this noisy baseline. Sometimes the baselines are not stable, they are up, they are down, like that, if you observe, right? This is because of if we are using uh, uh, a solvent that having a higher we can say UV cutoff, right? So at that time this type of observation uh, you observe during your method development, right? Then solvent use may cause a slight shift in UV lambda max from the publishing value. Of course, if we are using a methanol, if we are using a water, if we are using a ACN, that's slightly changing the lambda max value that with respect to the reported value. Okay. So these are the some solvent with their lambda max, right? And these are just general chromophoric groups like amine, ethyl, ketone, ester, nitro, right? And here I have write down the lambda max. So based on these oxochromes available in structures, we are generally assume that while present all these group, so that my compound is UV visible. The next is refractive index detector. If I wanted to separate sugars molecules like fructose, galactose, glucose, right? Some of the fatty acids like that, right? Then after polymers and alcohol. So at that time, UV detector is not capable of giving us the response because as we all know that in sugars, there is no conjugated double bonds. So there is no possibility of any UV light absorbance, right? But we know that a sugar having a different refractive index with respect to the solvent, right? If a glucose, if we are dissolve glucose in a water, if we are dissolve fructose in a water, these both having a different refractive index, right? So based on the refractive index, we are getting a response and we are separating our sugars compound while using this refractive index detector. Okay. So monitor the difference in the refractive index of the sample cell versus the reference cells, right? It is non-selective in nature because as we all know that refractive index change with respect to the temperature, right? If I am putting a HPLC in a room that having a temperature 25, and if room temperature is going to slightly high, means 28 or 29, then your detector is going to be changed in the terms of response of that particular peak. So we are not getting a reproducible result, right? So in industry generally they are preferring like that, they are maintaining a temperature of room as well while dealing with this refractive index detector. Okay, that's why it is non-selective in nature, because generally they are not preferring to use this detector. Concentration dependent, selectivity is typically 100 to 1000x multiply, right? Can't be used with the gradient. We cannot use a gradient system while separating of sugar molecules and all when we are using this refractive index detector. So this is the limitation of this detector, right? The same like is evaporative light scattering detector. As the name suggests, evaporative means evaporation of your mobile phase is going to be happen, right? Light scattering means there are a laser beam is there, right? So whatever our compound is there, they are in a droplet format and suspended into the gas stream, right? And they are going to be passed on that particular detector, that having a laser beam, and cut off that laser beams, right? And we are getting a results. So that's why they are known as evaporative light scattering detector, right? So it is ideal for the high molecular weight compound, sugars, carbohydrates, and less volatile acids, right? But the limitation is there. Solvent can be volatile for the best result. If our mobile phase is not a volatile in nature, right? Then we are getting so many noisy baseline, right? In our chromatogram, and we are not able to detect our main peak as well, right? So we have to incorporate a mobile phase that having a evaporative in nature or volatile in nature. In that case, we are not generally preferring the phosphate buffer, because if we are done a volatilization of phosphate buffer, they are precipitate out, and we are getting some residue of phosphate buffer. Okay, so for that purpose, generally we are incorporating ammonium phosphate buffers, because these all are volatile in nature, or a mobile phase that is uh, without a buffer, right? That is compatible with LCMS as well. We can use all these mobile phase when dealing with this ELSD detector, right? Fluorescence detector is there. According to the nature of our compound, as we all know that vitamin B12 is there, it is fluorescence in nature. So for the estimation of vitamin B12, we are incorporating this fluorescence detector. The another drug is lubiprostone is there. It is in fluorescence in nature, right? So analysis of lubiprostone is done by the fluorescence detector. Okay, so if you see the monograph of this particular capsule or API, right, vitamin B12, lubiprostone, where you have to find a fluorescence detector in their assay sections, right? Why they are using the fluorescence detector? Just because of nature of that compound. Okay, and it is more sensitive when we are comparing with the UV detector. It is concentration dependent, operation similar to the UV visible detector, but the limitation is only the things, the compound having a fluorescence in nature, right? Then and then we can use this fluorescence detector. Selection of separation mode. There are two type of separation. One is reverse phase and the next is normal phase, right? It is generally depend upon the sample solubility, in which solvent your sample is going to be dissolved, right? If my sample is going to be dissolved on ACN, methanol, water, then generally we are preferring uh, reverse phase HPLC. If my sample is going to be dissolved in hexane, IPA, then we are preferring normal phase HPLC. Okay. Reverse phase is frequently used because 90% of our application are on reverse phase HPLC, because most of the compounds are soluble in methanol, ACN, and water. That's why. What is the difference between them? Mobile phase is polar in reverse phase, right? Stationary phase is non-polar. C18, C8, phenyl, butyl, methyl. These all are stationary phase considered as a less polar, right? And the sample should be soluble in water or any organic solvents. These are the conditions to use RPHPLC, right? And for normal phase, Mobile phase is non-polar. Stationary phase is polar, like silica, cyano, amino, diols are there, right? Samples should be soluble in hydrophobic solvents such as hexane. Then and then we can use non-polar HPLC. Why reverse phase the most popular mode? If we see the thesis of any M.Pharm students, our students are generally use reverse phase HPLC. Why? Because larger portion of analytes are water soluble, right? Wide range of stable stationary phase are available because columns are different. As we all know that C18, C8 are generally and widely preferred, right? Selectivity can be altered by changing the mobile phase because we have a variety of solvent available when we are dealing with the RPHPLC like water. Okay, then after ACN, methanol in water, we are using a various buffer because buffers are soluble in water, right? And for the normal phase, in mobile phase, generally we are using the IPA, hexane, right? So it is immiscible with a water or any hydrophilic solvent. Okay. Uh, our ultimate goal is chromatography is to resolve two or more compound into the separate peak. Means separation of peak, right? With proper retention time, with proper tailing factor, we want, right? In any chromatography. So there are certain equations. I hope that you all are well aware about all these equation resolution. What is resolution? What is capacity factor on and all? I am not taking time on that particular terminology. Just keep it over. The two thing is there selectivity, right? In any chromatography, we want selectivity. What is selectivity? Selectivity is nothing but the resolution. Resolution means a gap between two peak. We can say in a simple word, a gap between two peak, right? If we are getting one peak at 3 minutes and if we are getting a second peak at 5 minutes, then there is a sufficient gap between two peak. So in that case, we are generally getting a resolution, right? And selectivity. Okay. Then after effect of efficacy on resolution, right? Efficacy we are generally we can see while seeing HTP means theoretical plate number. If we are getting a higher theoretical plate number, right, in our chromatography, then we can say the efficient method, right? When you are injecting your sample in a HPLC, right? Then after you are doing integration of that particular chromatogram. During the integration, you will get a theoretical plate number, right? It indicate resolution, selectivity, and efficacy of your columns, right? And how we are improving that number by increasing a length of column or while decreasing a particle size, right? If we are increasing the length of column, what happen? Our drug is more interact with the columns, right? And during the interaction of our analytes with column, we are getting a longer retention time. Means we are separating 2 3 4 compound in a single chromatogram, right? Or we can reduce the particle size, so we are improving the surface area, right, in a column. So by this way we are increasing interaction of our mixture of compound with column and separate it out at a different RT, right? So this is on our hand which length we can use, which particle size we can use, right? According to a separations we want, according to the resolution we want, we are just changing the column length and particle size. Okay, during the method development. Capacity factor is nothing but the retention time, right? So capacity factor generally depend upon a mobile phase strength because by this way we are changing up retention time. So capacity factor depend upon the mobile phase strength. So these are the terms that correlate with our method development parameter as well. Okay. The next thing is effect of column temperature, right? If we are changing a column temperature, we are getting a different retention time, right? Why? If we are increasing the column temperature, as we all know that if in my mobile phase that having a water, methanol and ACN, while increasing the temperatures, they are in volatile in nature, right? They are going to be volatile. So generally they are decreasing the viscosity of my mobile phase, right? So while reducing the viscosity, we are getting a less retention time of our compound, right? Even though we are increasing the sharpness of our peak as well, right? So column temperature also play an important role, from where we are getting a retention time of our peak as well as the peak shape, right? By this way we are reducing a temperature as well, sorry, column pressure as well, right? If we are dealing with the UPLC, where a pressure is having 1000 bar and above that, right? Where we are using a 1.7 micron column and all, right? So if we are getting a higher pressure in a UPLC, so while incorporating a column temperature like 40, 45, we are just reducing a column pressures, right? So it is one of the important parameter when we are dealing with a UPLC. Okay. The next is column selections. Which column is suitable and which column is not suitable, right? These are the questions are generally arise in our mind. So a selection of column generally depend upon the nature of our compound, right? By increasing a stationary phase with carbon loaded, we are increasing the non-polarity of our columns. Suppose C18 column, and if we are comparing C18 and C8 column, so C18 column is more non-polar in nature when we are compared with the C8, right? And compare with the phenyl. So what amount of non-polarity we required, what type of our compound is there, like it is in basic in nature or acidic in nature. According to that, we are generally selecting our column, right? Nowadays, there are so wide range of column available, like bonded column is there, right? Phenyl group bonded column is there. Then after there are certain bonding, like if we are dealing with the ion exchange chromatography, so some of the ion exchangers are bonded with the silicas ended, right? So according to our nature of analytes, we are selecting a column. pH is also suitable with respect to our column behavior, because if we are dealing with the higher pH, right, above 7 or 8 or 9, right? So generally a column is made up of silica, right, bonded with some of the functional group. But if we are using a mobile phase pH having in a basic side, means pH above 7, that it will leads to the dissolution of our silica, that will damage our column, right? So if we can say that my column is sustains for the 1000 injections, it will be destroyed within 200 injection or 300 injections just because of dissolution of silica, right? And what happen at a lower pH, means lower the 1 pH. If we are generally incorporate 0.8 pH, 0.5 pH and all, so at that time acid hydrolysis of bonded phases happen, right? So by this way we are generally damaging our column and all. So by if we are damaging our columns, even though we are not getting reproducible results, so during a method development, we are generally preferring a pH range which is suitable for our column as well. Okay, it is 3, 4, 5, 6 and all. Right? Some of the factors that influence a column life. So if we are uh, uh, preserve our column in a longer lifetime, then we have to incorporate temperature that having a lower, means not more than 40, right? low amount of buffer we have to use, like 10 to 25 millimolars, and high amount of organic solvent that we have to use, like 50 above 50% of methanol and ACN in our mobile phase. So by this way, we are increasing the lifespan of our column. Okay. So this is the summary of our method development. First, we have defining our goal. Then after gathering the information, select the mode, adjust the capacity factor. Capacity factor is nothing but the RT. Adjust the selectivity. Selectivity is nothing but the resolution, right? Efficiency means theoretical plate, right? And when to know where I wanted to quit, right? Sometimes it would be happen that generally students are try to develop a method on using only the water and methanol, right? They are changing the composition like 60%, 40%, 20%, 40%, 50%, 50%, and all, even though they are not getting any proper results. So you should know when to quit, right? You have to quit that water and methanol mobile phase and incorporate some ACN or some particular pH, right? So by this way we are decreasing our time to develop any method, right? Not only the time, we are decreasing the wastage of our costly solvent as well. Okay, so by this note I just end up my presentations and just taking 2 or 3 questions that I have written over here. If you have some questions like which is the suitable pH for the separation of mixtures containing acid and basic compound, right? If you have a compound, if you have a mixture, one drug is in acidic nature and another drug is in basic in nature, and these two drugs having a different pK, one drug having a acidic pK, the another drug having a basic pK, then what should I do? Which is the ideal pH that I have to use, right, in our mobile phase? These type of questions are generally arised. So at that time you should use start your method development at a lower pH, right? So at a lower pH, suppose 3 pH that you have to start, right? So at lower pH, your basic compounds, right, eluted first, because they are in ionized state and they are eluting first, and your acidic compound is eluted later, right? So by this way you are separating your both the compound. Okay. The another question is, if my drug is having a pKa 5, then what is the ideal pH of mobile phase? As I told you that never use a pH of mobile phase that is similar to your pKa. It may be a 2 unit different, right? And as we all know that in a reverse phase HPLC, acidic condition is more suitable, right? So we should start our method development of a drug having a pKa at around pH 3, right? So by this way we are just decreasing your efforts, and you are developing a rugged and reproducible method. Okay, thank you all. If you have any questions, if you have any questions from the student side. Okay, fine. I hope that you all are come away with the useful knowledge, right? And whatever the thoughts I have delivered to all of you, you all are keep in mind while developing your method on HPLC, right? And I hope that you all are well aware about these parameters and its importance when we are doing a method development on HPLC. Thank you. Thank you all. Thank you, sir.
Okay, thank you, Ravi sir, for such a wonderful session. I think some of the points are very well important while doing a method development, such as you have explained regarding the concept of PK, as well as various detector that you have covered, uh, which detector you can use according to the drug, whether the drug is acidic, basic. So that concept is really, really amazing. And thank you for accepting the invitation.
Thank you, sir.
Thank you very much, sir.
Thank you, sir. Thank you, sir, for giving me the opportunity to deliver my talk on this platform. Thank you.
Always a pleasure, sir, from our
Thank you.
side.
Thank you, sir.
Thank you
Now,
so much. Yeah, so we'll
end up
end
this
this.
session.
Yeah, yeah, we'll end this
Okay.
session.
Thank you. Thank
Okay.
you all. Thank you, students.